China didn't just build a road that generates electricity. It deployed 1.7 gigawatts of highway integrated solar across 17 provinces by the end of 2024, with storage, electric vehicle charging, and zero-carbon corridors already operational. America's response was no federal program, no design standard, and a single 1-megawatt pilot in Nevada. What China actually built and how reveals a strategic gap most people have not begun to grasp. Official statistics from China's Transport Department Research Institute show that by the end of 2024, the country's highways hosted 1.7 gigawatts of solar generation, more than three-quarters of all distributed renewable energy in the transport sector. This figure is not an isolated claim. The China Academy of Transportation Sciences, in its 2025 Outlook, confirms the same capacity and sector share. Cross-checks from industry sources and provincial tallies echo these numbers, placing highway-linked solar at the center of China's transport energy transition. This 1.7 gigawatt milestone signals a move far beyond demonstration projects. It reflects a coordinated infrastructure program spanning 17 provinces, backed by national policy and regularized data reporting. The Transport Department Research Institute and the China Academy of Transportation Sciences both serve as primary data collectors, aggregating project inventories from every region. Their datasets show that as of January 2025, highway solar installations accounted for 76% of the sector's distributed renewable energy, an overwhelming majority. The remaining share is split between rail, port, and airport installations, none approaching the scale of the highway build-out. The implications are substantial. China's transport sector now treats highways as energy assets, with gigawatt-scale solar capacity integrated directly into national statistics. This is not a patchwork of disconnected pilots, but a deliberate, system-wide model. The government's 5-year plan mandates renewable integration in new highway projects, and provincial authorities match central funding with their own capital and grid incentives. The result is a national energy infrastructure that treats roads as power plants, not just conduits for vehicles. With 1.7 gigawatts already installed and a confirmed 76% sector share, China's approach is both measurable and replicable, a data-backed template for transforming transport corridors into distributed power networks. Measured outputs from China's flagship highway corridors reveal the scale and ambition behind the official statistics. On the Jinan to Weifang Expressway, a 68-megawatt photovoltaic system delivers an annual yield of 68 gigawatt-hours, enough to supply more than 4 times the electricity consumed by the entire corridor. During its first 14 weeks of operation, the Jinan E-Road segment produced 96 megawatt-weeks of electricity, demonstrating a rapid ramp-up even before reaching peak output. This is not a demonstration strip. The project covers full-length medians, service areas, and tunnel portals, all engineered to handle heavy vehicle loads and continuous traffic. Further south, the Jinan to Hefei zero-carbon highway extends 152.7 kilometers, integrating distributed solar along medians, toll stations, and service area rooftops. Official estimates attribute a reduction of 9,000 tons of carbon dioxide per year to these installations, though independent verification of the emissions calculation remains pending. The corridor service areas deploy battery storage at scale. One site operates a 9-megawatt, 18-megawatt-hour lithium-ion system to buffer solar output and support grid stability. These corridors are not isolated. They represent a model being replicated in provinces from Shanxi to Hunan. Each project reports its own capacity, annual generation, and carbon impact, creating a portfolio of data points that make the gigawatt claim concrete. The physical reality, measured in megawatts, gigawatt-hours, and tons of avoided emissions, underscores that China's highway energy build-out is an engineered infrastructure program, not a collection of pilots. On the Jinan to Weifang Expressway, the engineering challenge was never just about adding solar panels to the roadside. Project engineers designed a 3-layer structural system, with each layer addressing a different threat from the road environment. The uppermost surface is a transparent, high-strength concrete slab, formulated to handle compressive forces 10 times greater than standard asphalt, enough to withstand repeated heavy truck traffic without fracturing. Beneath this, a layer of tempered glass and polymer-encapsulated photovoltaic modules is bonded directly to the structural base. This middle layer is responsible for both energy generation and mechanical resilience. distributing wheel loads across the modules and providing a barrier against fire and impact. At the foundation, an engineered soil cement base reinforced with geotextile fabric absorbs dynamic stresses and prevents subgrade deformation. The entire stack is sealed with a dual polymer waterproofing membrane, tested to resist water ingress and freeze-thaw cycling, typical of northern Shandong winters. After an incident in 2018 involving surface cracking during a severe cold snap, engineers revised the mounting method and added a flexible polymer interlayer to accommodate thermal expansion and contraction. These safeguards are not theoretical. The surface system is certified to a static pressure of at least 10 megapascals, well beyond the loading of any conventional highway. Every element is designed with failure mode mitigation in mind. Drainage channels direct runoff away from the modules, and the slip resistance of the road surface is measured to ensure braking safety even in wet conditions. The photovoltaic layer is electrically isolated and shielded from de-icing salts, with grid connection points protected by surge arresters. Integration with battery storage and electric vehicle charging infrastructure is built into the service areas, allowing generated electricity to be used on site for lighting, signage, and vehicle charging. This approach turns each kilometer of highway from a passive asset into a distributed energy generator, engineered to survive the stresses of real-world operation and to deliver bankable, audited performance over decades. Shandong High-Speed Group stands at the center of China's highway solar expansion, operating more than 668 megawatts of roadside photovoltaic systems by late 2024 and targeting at least 1 gigawatt by the end of 2025. The group's public roadmap, confirmed in quarterly reports and industry briefings, outlines a steady pipeline of new projects, each one backed by provincial capital and grid access incentives. These are not isolated installations. Instead, they form a coordinated program that now stretches across 17 provinces, from Hunan's mountain corridors to the plains of Henan and the industrial arteries of Shanxi. Official statements and internal accounting reveal a striking benchmark. 40% of the group's total electricity consumption for toll stations, service areas, and charging infrastructure is already supplied by its own solar generation. This self-sufficiency ratio, though not independently audited, is calculated from on-site metering and facility-level demand logs. The group's ambition is to push this figure higher as new corridors come online, with each project delivering measured outputs and feeding into regional grids. The expansion is not driven by demonstration grants or short-term pilots. Provincial governments match central funding with their own subsidies, typically covering about 30% of capital costs for new roadside solar. Preferential tariffs and streamlined permitting further accelerate the pace. As a result, the sector's installed capacity is tracked in regular government tallies, with 689 megawatts confirmed by December 2025 and a 1 gigawatt milestone within reach. 17 provinces now report active construction of near-zero carbon service areas, integrating rooftop solar, battery storage, and electric vehicle charging as standard features. This pattern of scaling is engineered for replication. The technical standards and procurement models used in Shandong are being adopted by highway operators in other regions. Each province builds on the same template, adapting it to local conditions while maintaining the essential features: integrated energy systems, audited performance, and clear capacity targets. The result is a national pipeline measured in hundreds of megawatts each year, supported by a policy industry alliance that treats highways as energy infrastructure, not just transport corridors. Researchers at the China Academy of Transportation Sciences have mapped the upper boundary of what highway-linked solar could deliver. Their GIS-based workflow, detailed in the 2025 Technical Outlook, models every kilometer of the national road network, including expressways, secondary highways, and rural roads against solar irradiance, right-of-way width, and system efficiency. The result is a technical ceiling of 943.7 gigawatts, a figure that dwarfs the current 1.7 gigawatts already installed. At full deployment, this translates to an annual energy yield of 17,578 terawatt-hours globally, as reported in a joint study by Chinese and international academics published in Earth's Future. The methodology assumes 15 to 22% module efficiency, standardized system losses, and a conservative footprint for each installable segment. Even after accounting for engineering constraints and land use exclusions, the modeled capacity remains orders of magnitude above present levels. Market analysts project that the sector could grow from $50.6 billion in 2025 to nearly $90 billion by 2030, driven by replication of the Chinese template and the sheer scale of untapped road infrastructure worldwide. The numbers make clear that, in technical terms, the ceiling for highway solar is not a matter of incremental progress. It is a vast, largely unclaimed energy resource. No federal program in the United States mandates or funds solar integration on highways. Instead, each of the 50 state departments of transportation operates under its own rules, with highway ownership fragmented among states, local agencies, and private concessionaires. The Federal Highway Administration offers only grant-based pilots, and national codes like AASHTO omit any specifications for photovoltaic pavement or roadside generation. This regulatory vacuum means that even as China pursues a 3.6 terawatt wind and solar target for 2035, American highway projects remain limited to small-scale demonstrations. The Nevada Solar Road, at just 1 megawatt, stands as the largest U.S. example, orders of magnitude below China's gigawatt-scale deployments. Construction codes in the U.S. do not address the mechanical or electrical requirements of photovoltaic integrated roadways. Any attempt to standardize would require rewriting state-level specifications, a process that can take years, and that faces resistance from risk-averse agencies. Without a central authority or binding national standard, each project must clear its own legal and engineering hurdles. The result is a patchwork of isolated pilots, none of which approach the scale or integration seen in China. For U.S. policymakers, the options are clear but daunting. They must establish a national program with dedicated funding, update design codes to allow for photovoltaic integration, and create incentives for large-scale deployment. Without these steps, the gap will only widen as China moves toward a future where highways are not just roads, but energy assets supporting the next era of transportation. China's 1.7 gigawatts of highway integrated solar signal a new era, one built on replicable, engineered infrastructure, not experiments. For the United States, fragmented governance remains the barrier. As China's model scales across provinces, the real contest is not technology, it is the capacity to act. The gap widens with every passing year.